We've been exploring over the last few chapters about the discoveries of electric fields and magnetic fields. We've been able to create some relationships between the two, but we're going to finalize those relationships in this chapter on electromagnetic waves. We will do this by first looking at a set of four equations which we know today as Maxwell's equations. Then we'll look at the formation of electromagnetic waves and the energy that these waves can hold. We'll conclude the chapter by talking about radio transmitters. Let's start by talking about Maxwell's equations. So over the last few chapters, we've derived three different equations between electricity and magnetism. There is a fourth equation which we have not yet discussed, but it's a very simple concept and we've already discussed the basis of it. So the three laws that we learned are known as Gauss's law, where we can relate electric fields to electric charges. We also learned about Ampere's law, where we can relate magnetic fields to electric currents. And finally, Faraday's law, where we find an electric field is produced by a changing magnetic field. The final equation that we need states that there are no magnetic charges. In other words, there's no North Pole without a South Pole. So any magnetic field that passes through some area has to wrap around and come back into that area. So there's no net magnetic flux around a magnet. So that's what that final equation means. It's basically the magnetic equivalent of Gauss's law, but much simpler. Okay, so these equations were really good, and yet not all electricity experiments fit these laws exactly. There were some experiments that were still unexplainable. Towards the end of Michael Faraday's life, a young man by the name of James Maxwell came along and found the solution to these problems. He suggested that if a changing magnetic field can induce an electric field, then is it possible to have a changing electric field also induce a magnetic field? And if this is the case, then there would need to be a change to Ampere's law. But the question was, what is that change? So let's illustrate Ampere's law this way. Imagine you have a current in a wire that's moving to the right in this figure. Ampere's law states that a magnetic field is produced by this electric current. Ampere's law allows us to calculate that magnetic field using the equation given by his law. Excuse me. Mathematically, the calculation would work regardless of the surface you choose to calculate around. Surface 1 here is the surface we've seen earlier. Just a simple circle looped around a wire. But I can change the look of that surface to be more like a bowl, where this would be the edge of the bowl, but the surface would come down around here. Think of this like a bowl. Now, this would involve some more calculus, but the math turns out the exact same and you get exactly the same result. But now consider this shape where you have a capacitor with a current coming out of the positive end and into the negative, a current coming out of the positive terminal and going into the negative terminal. We can do exactly the same thing that we did in the last figure, drawing a path around current I. Ampere's law holds, and we can calculate the magnetic field around this path based on the current. But if we take surface 2, notice that there are no currents passing through surface 2. And yet there's still a magnetic field around the edge of surface 2. Ampere's law states that there would be a magnetic field. There should be a current then as well. But this figure doesn't agree. You have a magnetic field, but no current passing through surface 2. So Maxwell suggested that the area inside the capacitor in the figure produces something that's called a displacement current, which is just the motion of electric charges due to a changing electric field. Again, this involves calculus, so I won't show you those derivations here, but all of a sudden, all of the calculations and all of the experiments started to work. So James Maxwell added an extra term to Ampere's law. Ampere's law now includes the creation of a magnetic field by a changing electric field. And so we find that the sum of all magnetic fields parallel to the outline of some surface area A would equal mu naught times any currents enclosed plus mu naught times epsilon naught times any change in electric flux over the change in time. So the revised equations now look like this. Gauss's law relates an electric field to charge. There are no magnetic charges, or any magnetic fields leaving an area have to loop around and come back into that same area. Ampere's law states a magnetic field is produced by an electric current or by a changing electric field. And Faraday's law shows that an electric field is produced by a changing magnetic field. These equations describe all that we know about electricity and magnetism. And since James Maxwell is the one who made the discovery that completed the puzzle, we now know these equations as Maxwell's equations. But we'll see in the next video that the discoveries that led to these four equations also actually describe the motion of light and all other electromagnetic waves.